Welcome to the first lecture in the second lesson of the class EECS X493 Introduction to Lens Design. As you can see, we're going to still be talking about first order optics for at least the rest of today's lecture, although we will be talking about more realistic optical systems and doing some comparisons as we go through our next series of these small lectures. So let's look at tracing rays using what are referred to as the paraxial ray trace equations. Okay? And this is a figure very similar to, or possibly identical to, one we've seen before. So I have some idealized thin lens here, only concerned with its power, not its thickness, etc. So I'm not at infinite conjugates. I have a finite object distance and I have an image location. I have my slope angles u and u prime, and I have my distance between my optical system and my object, and the distance between my optical system and my image. Okay. When we're doing our paraxial ray tracing equations, what we're going to do is assume our surface is planar, as you can see in this figure here, but you'll also notice that the rays are refracting, bending when they interact with that surface. So effectively we're going to treat planar surfaces as having power. We're just going to, at least for now, ignore the actual sag or shape of that surface. The height of a ray at some particular point is simply a product of the slope angle and the propagation distance. And what we're assuming with our paraxial ray trace equations, with our first order optics, is that we have a collinear mapping, points in object space map directly to points in image space, ideally. Now, if we want to compare that to a real ray, in this particular case I've got a relatively thick lens simply to make it a little easier to see what I'm talking about, but we have collimated light coming in this case, but because this is a planar surface, all of the refraction is occurring at this back interface, and you can see that the rays are bent as they hit this interface. But remember, Snell's law says the rays are bent relative to the surface normal at the point of intersection, and as you can see from these different line segments that I've drawn here, that each of these rays are refracting at a different angle. Obviously that's going to be a lot more complicated for us to figure out rather than simply using a paraxial ray trace equation where we simply have our slopes and our distances. We'll also notice in the case of this real optical system we have an aberrated image. All of our rays do not converge to a common point, and the spread of this aberration, and if we assume this is a YZ plane projection that we're looking at the aberration in the Y direction. And if you think about it, if we were looking at an XZ projection, we would also probably see, or definitely see, aberration, in this case almost identical aberration, in the XZ plane. But in this figure, this is simply defining my aberration, which is the spread over which the rays reach at this particular image location, and right now this image is at the defined paraxial image point. Might not be the best image location for a realistic system, but for now it's simply at the paraxial focus. Now, when we go back into our paraxial ray tracing equations, what we again have is we treat our surface as being planar but having refractive power, and we have the slope that the rays make relative to a projection, and we have the distance that the rays travel. And again, in an ideal situation in this paraxial region, all of the rays will converge to form an ideal image. In this case, because I have collimated light coming in, I'm at infinite conjugates. This is going to be at the paraxial focus. It's defining the effective focal length of my system. Now let's take a look at doing a ray trace, and what we're showing here, again, our surface is effectively planar for our approximation, although I have sort of drawn the actual surface shape, the sag, here just to give a point of reference. But if we have some point source at some location, in this particular case it's at a near distance, but emanating from that point source location will be wavefronts, and those wavefronts ideally will be spherical. What we would also like ideally is once the rays or the wavefront, however you want to think about it, has propagated through the optical component, we'd also like to have spherical wavefronts converging towards our image location. Okay. In this particular case, we're assuming we're in the paraxial region, so we're only worried about slopes, heights, and distances. We're not worried about the sag itself. So in this particular case, I'm showing one ray that comes from my object point O and gets imaged to my image point O prime. Now, if we go back to Fermat's principle, Fermat's principle tells us that the path that the light takes to travel from one point to the other is that for which the time is at a minimum. Now, I talked about this ray right here, but we also have this ray right along the axis, the ray that goes directly from O through O prime, intersecting the lens at its vertex location. So you might want to look back at that figure while we're going through this, but based on Fermat's principle, these two distances must be equal. This path length must be equal to this path length. Okay? They might not look at it at first glance, but remember we're talking about optical path, so index will also come into play. Okay? Now we can also look that, we have 2 points on the wavefront, so we have the distance from O to P and the distance from O to A, which is where the ray intersects the vertex. Those, by definition, those path lengths must be equal. Similarly, BO prime must be equal to SO prime. So this distance must be equal to this distance. Again, we're at points on a common, defined as spherical wavefront. So we can do a little bit of mathematics, and I will sort of apologize right now. Well, not really apologize, but I will tell you that much of this week's lectures will be mathematical, if you will, but I promise this will probably be the last lecture that has quite this much math associated with it. Okay, so here's another calculation, and again, rather than flipping back and forth between the pages, you can take a look at what I mean by these distances. Now, if we take into account the paraxial sag calculation to sort of get an idea of what's happening right up in this region right here, this distance is referred to as the sag. The sag is a function of the surface curvature, which for temporarily we're ignoring, and the height of the ray off the axis. And similarly, again, this is simply using our paraxial ray trace equation. So if we put all of this together to calculate the optical path, and then do a little bit of combination, since these two are equal to each other, we'll set their relationships equal to each other, and do a little bit of combining and canceling out common terms. Notice how things get easier much faster. And we can see that the ratio of the second index to the image distance is equal to the ratio of the index in object space divided by the object distance plus n prime minus n, the change in index, times the surface curvature. And again, we're not going to deal with angles directly, we're just going to think about slopes. And our slopes in object space and image space are related to the height of the object and the object distance, or the height of the image and the image distance. And the whole purpose of this was to bring us approximately to this location right here that says n prime u prime, so the information about the index in image space and the slope in image space is a function of nu, the index and the slope in object space, minus the ray height, surface curvature, and the change in index. Why does this matter? Okay, if we follow the paraxial ray from point S to the image at O prime, it has a height h, and its slope is this u prime. That tells us then that L prime, the image distance, is simply minus h over u prime. In this case, h and h prime are the same. Now, how this helps us. Basically, when we think about an optical surface, we have an object and we form an image. But in reality, that's for one surface. If I have a lens, it has two surfaces. The first, I have an object that it interacts with the first surface and forms an image as a function of the power of that surface. That image serves as an object for the second optical surface, which forms an image that serves as the object through the third optical surface, etc. And we can just follow this through, simply applying this to successive surfaces as the light propagates from surface to surface to surface through your optical system. And that's probably enough math for right now, so thank you very much, and we will take up again shortly.